Hi, this is Sam Rashkin with Energy Star for Homes, and welcome to a presentation on the new version 3 specifications. And for the first time since Energy Star has been introduced in the market starting in 1995, what we can do now is assure performance with every labeled home. And over the next hour and a half, we'll cover how we can do that and how these new specifications bring complete building science to the housing industry for the first time. So let's start with what is Energy Star for Homes. Essentially, we do two things. We define truly energy efficient with our rigorous specifications that are third-party verified, and then we provide recognition to our builder partners with labels and a whole array of marketing tools that help consumers find them and help them, the builders, get special recognition for their commitment to the program. And all this is voluntary, so it means this has to work with the housing industry in a way that meets their business objectives. So that's what we do. And growth has been exponential since we got traction starting in 99, 2000, 2001. And we've grown to over 1.2 million homes. We took some drop after the industry slump took hold in 2007. But last year we started going back up again while the housing industry still remains at a very low number that continues to decrease. Look at the market penetration numbers that we've achieved, and the climb is showing that while the rest of the industry is slumping, it appears that the energy efficient builders are doing better. And an indication would be our 2007 market penetration, which was about 11% nationwide, grew to 17% in 2008, a 40% increase in 1 year, then grew to 21% in 2009, and last full year of recording the market penetration numbers, we're over 25% market penetration. That means 1 in 4 homes built in the U.S. last year earned the Energy Star. Tremendous growth in program and what's growing as well is the builder interest in the program. Before the market went soft, we used to achieve about 30 builder partner applications a month, and that's grown to as high as 300, settling in now in the 200s, but it's an incredible interest growth of about 1,000% that builders have with this program, again showing the connection between what we do and the builders. So if Energy Star is a solution, what's the problem we're trying to achieve? What performance issues are we trying to address? And it comes down to our core brand promise. We try to deliver truly energy efficient homes, much better than code. We must be cost effective, and we want to demonstrate performance that meets or exceeds expectations. That's a core to Energy Star. Winds up with homes that we deliver performance that far exceeds expectations. So let's talk performance issue. The performance that we go after is really the 4 cornerstones that are possible with comprehensive building science. They are affordable homes with low utility bills and maintenance bills, comfortable homes, room by room, floor by floor, healthy homes that are able to provide much better indoor environments for the inhabitants, and much more durable homes. They're basically by doing 3 things, or we don't get there by not doing 3 things, and those are airflow, thermal flow, and moisture flow. And moisture is broken into vapor and bulk moisture. So if we just do building science parts and not a complete system, we won't have complete control of those 3 key elements, and therefore weeks for failures. And let's review how these tend to occur. And let's start with air leakage. Essentially in air leakage, there are key points you have to know are the most critical. One of them is the sill plate to the foundation and sill plate to the flooring. Here's a great image, an infrared image, that shows just how much air leakage occurs at sill plates that are not properly sealed. And many homes, if not most of the homes around the country, were built without good sealing details. This is an image that's an infrared image. In an infrared image, the light colors show warm surface temperatures, the dark colors show colder surface temperatures. So when you see this much dark colors, it shows evidence of air leakage. In this case, now doors and windows and sill plates represent about a half-mile cracks in an average home, and here you can see how much doors and window openings are so critical. The reason they are is that there's a ½ inch or so rough opening gap around every door and window that must be fully sealed for them to work. Another major gap that's less understood and only recently been thought of as an important building ceiling detail is the air gap between the sheetrock and the top plate, where there's an adjoining attic above. Attics can get extremely hot and cold, creates tremendous pressure differences, and that can result in substantial driving forces at that gap. This image shows just how much the cold attic air is coming down behind the sheetrock at that gap. Another source of air leakage is just through the penetrations, which are numerous to the attic, and sometimes leaky ducts in the attic that can lead to ice damming. The warm air tends to melt the snow that's on the roof, and when the melting snow gets down to the eave that's freezing again, it forms ice, and that blocks the snow melt, and which can go up underneath the roofing and create all sorts of damage. So very critical to control air leakage at all penetrations and duct leak as well. Okay, next item is installation problems. This is very significant problem because across the country installers are paid by the piece and not by how well the insulation works. So the key criteria for many jobs is how fast it can be installed, not how well. And the key problems that tend to surface, particularly with batt insulation products, are gaps, voids, compressions, and misalignment. Misalignments when the insulation will not touch the air barrier surface. That leaves an airspace that can lead to convective losses that substantially undermine the insulation performance. So these 4 critical components must be addressed for insulation. And a gap like this in a wall will show up very prominently in an infrared image. This is a gap in insulation between the framing member and the insulation. And how long will that gap be there is a key question to ask, and the answer will probably be for the life of most buildings. People don't tend to rip off their sheetrock and try to fix insulation problems. It's very cost prohibitive in most cases. So these are really important details to get right at the beginning when we construct our homes. That's the time to do it correctly. So here's a typical type of compression detail, and then it will show up and last forever in this wall assembly. Another way that we get misalignment is just some practices are inherently going to lead to it. This is something called inset stapling, where paper face batt insulation, the installer staples the tab of the paper facing to the inside surface of the stud. This is done often ostensibly to leave the stud face exposed for gluing and nailing the sheetrock, but sheetrock can be installed without the gluing and work just perfectly fine. So what we wind up doing is accepting a systemic misalignment or airspace between the sheetrock and the insulation. Here's why it occurs, or how it occurs, and it's so important. Here's a typical inset stapling job, and if I were to highlight the air spaces on either side of the insulation, what you see, there are big air spaces on both the interior and the exterior side. So imagine, if you will, an extremely cold, below freezing winter day, and you have these air spaces. The only thermal resistance between the outside airspace and the outdoors is the sheathing, building paper, or house wrap and siding. And that's not very much thermal resistance. So it's very likely that that airspace adjoining the outside wall on a below freezing day itself would be about freezing. And on the inside airspaces adjoining the sheetrock, there's very little thermal resistance from sheetrock, R value 0.5. So the inside air spaces, when the rooms are 70 degrees, are likely to be in the mid-60s. So I have outdoor spaces in the mid-30s, indoor spaces in the mid-60s. I have a very substantial driving force from more heat to less heat that's going to induce a convective flow, and that convective flow can effectively bypass the intended purpose of it. And this shows you how it can manifest itself in a winter day with an infrared image where the very light colors indicate virtual heat explosion out of the house and the insulation hardly working better than the wood studs between them. the very, very white colors at the top and bottom of the walls, probably evidencing some sort of voids, are just going to hyperdrive this convective flow even further. The wall should be the same color as the roof shown at the bottom of the image. There is a significant problem here because of the systemic misalignment of the insulation with the inset. Another critical area where we see real problems is insulations installed in band joists, often with substantial gaps, voids, compressions, and misalignment. You can only imagine the surface temperature on the outside sheathing on a below freezing day is extremely cold. The airspace in the framing space between the floor above and the floor below, called the interstitial space, is probably the same as the rooms themselves. So we have a 65, 70 degree space in the floor. We have a freezing temperature in the outside wall. We have all these air pockets and openings for the air to get to the outside wall. There's probably no chance that the outside wall is not experiencing condensation with the warm air meeting a cold surface. This only means that the potential exists for mold and moisture. That will only occur if the wetting exceeds the ability for the material to dry. But it's a risk we don't need in construction. We need the insulation to work, to be, again, no gaps, voids, and compression. And we would love to see no. Again, the infrared image is a very, very strong evidence of a significant problem. Here you can see the band joist, again, exploding heat from the inside to the outside because the insulation is not working in that. Another significant detail occurs with misalignment at the ceiling. One evidence of this is just a silly detail that happened by a builder, well-intentioned, trying to cover the framing members for a false slope ceiling with insulation running across the framing members to block the thermal bridging at that member. But a very big misalignment space was left between the insulation and of course the ceiling goes into extremely hot temperatures, in this case in a very hot Arizona summer. So the builder's good intentions were undermined by leaving a very significant misalignment. Another case of systemic misalignment is the practice that used to exist, or maybe still exists in the Northeast, and particularly the Boston area, where they use strapping below the ceiling framing. Ostensibly, I think it's to allow for space around the wiring without drilling the framing members, but this is a consistent air space between the insulation now and the sheetrock below. So what will happen if we come back with the infrared camera is see a very cold ceiling in the winter. So this is very, very indicative of the importance of getting the insulation right without gaps, voids, compression, and particularly misalignment. We also have significant thermal holes between the home and the attic that occur at attic hatches, drop-down stairs, and vertical access doors between living space and attic knee wall. And so here's an indication of the big thermal hole at an attic. Also, we have very significant misalignment problems where insulation's on a flat condition, such as a floor above a garage that's a bedroom, might be a bonus room, or a cantilever. And essentially what happens is, in the summer, the heat can flow around the insulation like it's not there and create a hot floor. And garages can get as hot as 105, 110 in the summer, and that can be a very hot floor that's in the bedroom above. In the winter, what happens is that the much warmer air or temperature in the room wants to go to less or lower temperature in the garage, and the heat can flow right out, almost like the insulation's not there when it's misaligned with the floor, winding up with a cold. So there's no chance, if we look at images all across the country of typical practices, that this insulation detail would be touching the floor. And when that happens, you wind up with a cold floor in the winter and a hot floor in the summer. This is a winter image of a cantilever floor. The only reason there's any light, color, or warm surface temperature being indicated, as you can see, the heating duct runs into the cantilever space. But any place else, it's a very cold floor. And to show the importance of the whole system, here's a house where the walls actually look really good in terms of very little heat flow coming from the walls. The window treatments at the windows seem to be doing their job. And then you get down to the slab edge at the very bottom, and you see almost like a super highway flow of heat from the slab out to the cold winter condition outdoors. And this again is a winter image showing how important slab edge insulation is, and where everything else is done very well, we'll wind up with an extremely cold slab that effectively will be almost like sucking heat from our body, because mean radiant temperature dominates comfort. And we'll still feel cold even though the room has a desired ambient temperature. So we have to get the whole system right, or the whole system can fail. Air barrier problems are also quite simple. In this case, fibrous insulation does not equal an air barrier is the key point. It'll stop thermal flow, but air can go right through fibrous insulation enough to really derate its effective performance significantly. So we needed a 6-side air barrier around fibrous insulation for it to work, and that air barrier has to be in contact or alignment with the insulation. So here's a good picture showing just how important this is. This is a very good installation, actually, of fiberglass insulation between the framing forming this attic knee wall. Yet when we lift up and look at the fibrous insulation, the fiberglass insulation, you see how dark and discolored it is. The driving force is creating airflow through the insulation, so much so that it becomes this high efficiency filter trapping tremendous amount of dirt. You need a backside air. And just as a good indication with an infrared image, first here's a regular shot of a room with a double height ceiling and attic on the other side. Come back with the infrared image. This is a summertime image, and the hot attic is actually imposing a hotter surface temperature between the 2x4 framing used for this attic knee wall. In other words, the R3.5 studs are much cooler in temperature than the space between them that has R19 insulation. The insulation's not even working at a fraction of its rated value because it does not have a complete assembly. And to show you it works both in the winter and the summer, here's an attic knee wall in the winter, and the R19 insulated space between the 2x4 studs is much, much colder in surface temperature. So again, the R19 insulation is far, far below its rated R value in terms of effective R value. You need. And just to beat this one even further, here's a picture of a bedroom. On the back side of this wall where the bed sits against, there's a slope ceiling going down to an attic knee wall space above a garage. And if we come back with an infrared image, we can see without the backside air barrier on the insulated wall, there is a very, very hot wall, probably above 90 degrees. You only can imagine the discomfort for the occupants sleeping in this room. So in addressing a performance complaint, the air barrier was installed on the back side, and now the wall temperature is completely in control. Just a great series of images to show, one, the problem, and two, that the building science principles really work. If you do a complete assembly, you will stop the air thermal. Another key detail for stopping airflow is, or convective flow, is where insulation runs right up into the eave. If you just let it run right to the eave, there's a lot of airflow between the gaps at the roof sheathing and the fascia board and the soffit, and often there are soffit vents as well, and the air rushing through the eaves, because it doesn't stop airflow, undermines its. So here's an attic eave surface from the interior in a cold winter day. You can see how cold it gets. In summer, it's almost like a strip heater, with the hot temperatures affecting the very complete edge of the building. So very simple little details are so critical to the whole. Here's another detail where the drop ceiling occurs, and the insulation is going to be run right across this space without a lid. And the reason that's so important is it effectively leads to a thermal bypass without the air barrier. So there's the air barrier that should be there, but it's missing. And what's happening, let's say, is the freezing day occurs, the attic and the outdoor will be about the same freezing temperature, while the inside's about 70 degrees. And then, therefore, the air temperature inside that drop ceiling space is likely to be the same as the inside, since the R value of sheetrock, again, is only about 0.5, doesn't stop thermal flow. So now we have 70 degree air in the drop ceiling, we have freezing air in the attic. the driving force is to go from more to less, and we have fibrous insulation that doesn't stop airflow effectively. So you start the first part of a convective flow, and one in equals one out. So if the air is going convectively into the attic to go from more to less, an equal amount of air will come from the attic into the drop space to create a balance. And ultimately you get a happy midpoint where it's still a very cold surface temperature level for the indoor condition. On top of that, airflow can go through the insulation to the outside wall where it can meet a cold surface and possibly condensate for further moisture problems. So this is thermal bypass completely conceptually shown, and this is it shown in an infrared image. Virtually what you can see is with the lid missing at the arches and drop ceilings, you essentially have a complete thermal connection between the attic and the house, so much so that you have cold surfaces everywhere that will create a significant discomfort in the house and higher utility bill. And to show where it works equally well with both heating and cooling, here's a drop ceiling getting extremely hot in a hot condition. Okay, thermal bridging problems are another part of getting a thermal enclosure right. Thermal bridging occurs when poorly insulated members or lack of insulation allows for thermal flow that's unintended. So this is much more wood than we need to hold up the house and will display insulation. Again, a lot of wood being bundled up that doesn't need to be there for stress, but creates a very big thermal bridge where, again, in this picture in the winter, you can see how much heat's coming through the wood studs much more quickly than it would. Another issue where thermal bridging occurs is at corners and wall intersections. In this corner, which is very typical in construction, you have three studs. The two key studs that are there for the sheetrock to be nailed to are two of the three studs, and then one stud on the outside is the third stud. This creates an open space that's not insulated. And secondly, what it creates is a nailing surface for two different studs for the two different pieces of sheetrock. Wood today is much more moisture content. It's much less dimensionally stable. So the outcome is we wind up with cracking that can occur at corners much more readily with this detail and an uninsulated corner. The infrared image again shows just how cold it would be in the winter. Flip this in the summer. The same thing happens at wall intersections. Here's an infrared image that shows where a wall comes into the from inside to the outside, and again the studs create an uninsulated space that shows up on an infrared image. And lastly, with thermal enclosures, advanced window problems need address. Essentially old windows that are not high performance low E windows let much more heat flow through them than a low E window, and we can do much better. High performance windows are well established in the market. Now let's move on to the HVAC quality installation side of things. There's a very significant performance problem because we install HVAC systems today based on lowest cost and not performance. Often what happens is that the builder and contractors are negotiating the lowest possible prices and not working to achieve performance. Again, much like the insulation contractors paid for. So essentially what happens is you pay for 13 and often get effectively maybe 8.5 or 9 because those performance issues have direct and real impacts on how well the system works. So here's some examples of other issues that have to do with quality installation. The distribution system problems. Leaky ducts mean that the air that's heated and cooled doesn't get to the also ducts that are laid out without proper design and installation create significant problems. Here we're trying to get from point A to point B. The system is a flex duct system. Flex duct comes in 25-foot rolls, and there's an amazing coincidence. It always takes 25 feet to get from A to B when you use flex duct. And unfortunately, that means you'll probably be hardly any air coming out at the register of B. The reason is, one, the 25-foot length itself is very long when you only need 4 or 5 feet. Two, every bend in flex duct creates like a 6 or 8 foot equivalent length on top of its 25-foot length. You have almost a system here of like 70-80 foot of effective duct length. I would submit there's hardly any airflow getting out of B. A very significant installation and very common. Also, we don't watch how ducts are installed. They get compressed and lose their ability to maintain proper airflow. or they get pinched so that they almost function like a garden hose that's being squeezed to stop water flow, but in this case air. So very significant distribution problems. And then there are ventilation problems, because we're building homes with better insulation. We need to make sure that the moisture and other pollutants can get out of the homes and are diluted effectively. When you see condensation, it's a good indication that you do need more ventilation. But even if you don't see condensation, homes have a lot of chemical content in them, formaldehydes and VOCs, also radon, dust, particulates, pollens. All those need to be filtered down, diluted, and ventilation systems are very that. And then there are pressure balancing problems in homes if they're not properly installed with all the systems and fans that go into them. A good indication of a problem occurs when you see this kind of dark line in the carpet below a bedroom door. That indicates the air is trying to get out but can't get out. And the reason the air is trying to get out is we typically build with central return. So the rooms have air being pushed into them through the ducts, and then the air can't get back to the central return when the door is closed. So it creates pressure imbalance between the bedroom under positive pressure and the central spaces that will wind up under negative. And this is a diagram of how that happens. If the doors are closed, the air handling unit keeps pushing air into the bedroom that can't find its way to the central return. Now what happens is it's almost like blowing up a balloon. The more and more the balloon fills and is pressurized, the more effort it takes to blow the balloon. I can take more effort blowing a balloon, but the air handling unit cannot suck up more energy and blow more air into the bedroom when the pressure builds up. So as a result, you stop getting as much heating and cooling and dehumidification in the bedroom when the door is closed, which can lead to setting thermostats higher in the winter, lower in the summer. It can also lead to compromising some rooms' comfort to benefit other rooms. And the central spaces, of course, wind up also being more negative pressure, which can create other conditions as well that we'll look at. Here, for instance, is what happens, for instance, when a bedroom door is closed for about 20 minutes. You have the doors open on the left, and you have the surface temperature of the ceiling about 76 degrees. And when the doors close and the central space goes into negative pressure, now the additional negative pressure is pulling heat from the attic through these light fixtures and raising the ceiling temperature just over those 20 minutes 2 degrees. Another example of how this works at the gap between the sheetrock and the top plate is when we close the bedroom doors and this wall area in the family room in the central part of the house that's under negative pressure, the wall surface temperatures start experiencing increase due to the air being pulled in at the gap between the sheetrock, going up 2 or 3 degrees. The pressure balancing issue also includes how we must think about what happens by the appliances that we choose and how we locate them next to other appliances. Here's a clothes dryer. Clothes dryers usually are about 150 to 250 CFM of fan flow to pull air into them and remove the moisture in the clothes. Now, next to the clothes dryer, you'll notice there's a gravity exhaust water heater, and if the clothes dryer is pulling in, let's say 200 CFM for a 60-minute cycle, that's 12,000 CFM, 12,000 cubic feet of air that's being pulled in, and a substantial potential negative pressure right there adjoining the clothes water. And if we look at the top of the water heater, there's a big hole right at the exhaust manifold, the exhaust hood for the water heater, and it's a tremendous ability to pull those exhaust gases back into the house, which are not safe. Good indication at the bottom of the water tank that we have a problem is the flame rollout that appears to be occurring by the burnout stain right there. So tight home and good insulation, let's add pressure. Here's a wall that's a family room with a laundry room on the other side. You'll notice that with the dryer vent going from behind the dryer in that wall up to the attic and out the soffit, there's always under a very hot attic condition, a hot surface at the dryer when it's not operating. They operate the dryer for 40 minutes, and what happens is now we need again that 12,000 cubic feet or 10,000 cubic feet of air, and the air is going to come from the path of least resistance. In this case, the gap between the drywall and the top plate allows that wall temperature to get as high as 90 degrees in some spots, which again will compromise comfort. And lastly, the filtration problems when it comes to HVAC systems. They're very cheap and poorly installed without an effective frame to stop airflow around them. So it's bad enough the filter itself doesn't do a very effective job. The air can bypass them as well going around the sides and the tops where there are big air gaps. So the filters in our homes aren't doing a good job removing the particulates in the airstream going through the and leave lots of particulates in the air beyond. And then there's the water management system and how important comprehensive systems are there as well. And to think about this and how important it is, let's take an example of when you take a shower and want to dry your hair with a hair blower. You can dry your hair probably in just a few minutes. Now stick a piece of insulation board product between the hair blower and your hair, and it'll take hours if you can dry your hair at all with that piece of insulation between the hair dryer and your hair. And that's what's happened to these high performance homes we're building with these rigorous specifications. They're so well sealed and so well insulated, they have no tolerance for drying. They don't experience the same thermal flow, and if they get wet, you will have much greater risk, if not certainty, of moisture problems. Therefore, it becomes incumbent on an energy specification like version 3 to think about the fact that we have to, and effectively what we have to do is look at the whole system, draining water from the roofs, the walls, and that includes the wall openings and the foundations, and protecting materials and selecting materials properly so our homes can perform without moisture problem risks. So here's a typical, let's not call this typical, but here's a house without any drainage plane. Here's a home that has, for some reason, flashing around the windows, but no drainage plane on the walls. So effectively, if moisture gets behind the siding, you have a very serious condition for getting the, in this case, OSB sheathing wet. And the problem is that all cladding systems get wet behind them. Brick, stucco, aluminum, vinyl, wood, every siding material virtually gets moisture behind it. And we should make sure every home, also every window leaks. It's just a matter of just something that's going to happen, and we need to prepare for that. Without pan flashing at windows, the leakage will get into the framing around the window and the siding and potential damage. Here's just one case of where it was enough wetting that the material couldn't dry and it led to mold and dry rot problems. And also the slits that are in foundation drains, which are intended to collect the water and remove them away from the foundation, also can let sediment in. And over time, 7-8 years, these drain tiles easily can clog and be virtually useless for draining water from the foundation, their purpose for being installed in the first place. Since most homes last 100 years or longer, it would make a lot of sense to install drain tiles that don't. And then there are flashing details that are just so basic but are ignored. Here's a roof adjoining a wall, and the water runs right down against the roof behind the siding. And like we said, all sidings leak. We should be diverting the water away from the wall so it doesn't run into. And again, an infrared image shows a good example of just how wet it gets at this juncture. And then we should be protecting materials on site so they don't get wet in the first place and can be installed much drier than would be exposed. Okay, so those are the performance problems we think need to be addressed for assured performance with every home. So in solution, and that's what we attempted to address with the Energy Star version. And the key point we want to make here is that based on what we've shown you, parts will not get her done. It's not a question of getting a maximum HERS score or percent above code or a minimum number of green points. None of those get you complete systems. And this we chose for complete systems was to look at what we need to do for airflow, thermal flow, moisture flow control, and make sure everything that was necessary for a complete system was included in an Energy Star version 3 specification. So the underpinning for what we did with our specification was to start with airflow, thermal flow, moisture flow, then make sure equipment was efficient to minimize the loads, and then the third party. And so version 1 came along, and we started the process. We got great air sealing details systemic in the housing industry. We established tight ducts across many, if not most parts of the country, introduced low-E windows in many regions where they were not even a consideration. We made sure to enforce insulation R values at least at code. We started with efficient heating equipment in cold climates, cooling equipment in warm climates, and the HERS rating process. Along came version 2, and we introduced the thermal bypass checklist, which ensured complete air barriers and alignment with those air barriers. And then we also started looking at right sizing of cooling equipment, and on the prescriptive basis at least, ensuring efficient lighting and appliances. And then version 3 comes along, and effectively we complete the building science picture. It's now comprehensive and completely assures performance in every labeled homes. Under airflow, we added pressure balancing so the air can get from the central to the central returns from each of the bedrooms. We also made sure under thermal flow that insulation was installed properly and that we address thermal bridging. Under moisture vapor, we also added whole house and spot ventilation, and we ensure that the equipment can handle the dehumidification requirements in hot and humid climates. And under bulk moisture, where we had no measures, we now have complete bulk moisture control with water managed roofs, walls, foundations, and site, and building materials that are protected and used and selected properly for their function. Under equipment, we also look at HVAC systems not to be just efficient, but to be installed with quality installation practices established by the industry and manufacturers themselves. And then under third-party verification, we added 4 checklists to replace the thermal enclosure checklist. Basically, the thermal enclosure checklist addresses all the red boxes that we just discussed, and because the checklists are mandatory, every house has all those improvements: air sealing, air barriers, low-E windows, insulation R value, installation practices, alignment, thermal bridging. Under HVAC quality installation, we now include tight ducts and pressure there, along with pressure balancing, right sizing of the equipment, whole house spot ventilation, and we look at the dehumidification is provided, and HVAC quality installation. And under water management checklist, every house will have water protected assemblies and materials that are properly selected. You also notice the house size is part of Energy Star version 3. As homes get bigger than an average size home, they will be required to be more efficient. So the only real wiggle room left in the Energy Star version 3 is the degree of efficiency of heating, cooling equipment, water heating, lighting, and appliances. All the colored boxes are insured with every labeled home. This is why we can promise now for the first time assured performance with every Energy Star qualified home. Now the way this works is, first is a baseline specification that ensures the homes are at least 15% or more efficient than code. And we get there with the same basic requirements that are from the older specification versions: efficient heating and cooling, efficient envelope, efficient components. Now you have 2 ways of doing it, just like you have in the past, to get to this baseline: prescriptive or performance. If it's prescriptive, you just do the baseline specification that are there, those measures that are included in that reference design specification, and you can only do it if the house size is less than or the same size as an average size home called the benchmark home. Now the performance path, there's a variable HERS index score that's custom developed for each house by the computer software, and in addition, a size adjustment factor is applied if the home is bigger than the benchmark home. This is why you can only use performance if your house is bigger than the benchmark home, because the size adjustment factor has to be applied. Now you can not use renewable energy for that meeting your variable HERS score. Again, on the performance path, a software package will determine a variable HERS score for your house. You cannot use renewable energy systems for the points needed to achieve that score. However, where extra points are needed for the size adjustment factor, renewable energy is allowed, but only for the incremental points needed for the size adjustment. When you get to this baseline level of performance, then the mandatory checklists kick in. 1 for the thermal enclosure, 2 for the HVAC quality installation, and 1 for water managed construction. The 2 for the HVAC quality installation, 1's for the contractor, 1's for the HERS rater. So these mandatory checklists are the thermal enclosure system, the HVAC quality installation system, the water management system, and together they ensure complete building science. We're going to go through the basic requirements of each of those to complete this. So the thermal enclosure system, the first component you want for a complete system is complete focus on air leakage, so you have a very airtight home. And we know where the big holes are. The shafts or chases have to be completely flashed and sealed. Those could be for flues, for chimneys, they could be for duct shafts, plumbing shafts, whatever it may be. Every shaft or chase between an interior condition and an exterior condition like an attic or a crawl space have to be fully flashed and sealed. All the access panels, whether they be an attic hatch, attic drop-down stair, or an access door to an attic knee wall space, have to be sealed and insulated. The drywall gap at the top plate has to be fully sealed. All penetrations for electric and plumbing have to be fully sealed, and all the cracks around windows, doors, and sill plates have to be fully sealed. So, typical details, but together now you have to do a visual inspection of them as well as the blower door test to make sure that the house is tight. So this is one way of going to air seal the gap between the drywall and the top plate. This is a foam seal at the top plate that's being done, and this is what it looks like with an applicator putting it at the top plate as well as some other places around the windows and doors. Another way to go is on this detail is to seal the gap from the top with a spray foam or equivalent sealing technique. So here you can go at it from the top. It's more about the what than the how. We want to make sure there's no airflow between the gap between the sheetrock and the plate. And there's a picture of sealing it from the top that was actually done in a retrofit application that can be just as well done in a new. Then insulation R value, which is quantity, and insulation installation, which is quality. We are technology neutral or material neutral. We don't care what material you use. We care about the what. No gaps, voids, compressions, and misalignment. Basically, it has to be ResNet grade 1 level insulation. The only exemption is where rigid insulation is used on the outside wall. The wall itself can have grade 2 insulation installation at that detail. A very critical part to be mindful of is the band joist. It requires grade 1 insulation, and it's almost impossible to do with traditional materials. We recommend spray foam. Definitely bats are going to be very problematic, but it has to be grade 1 at the band. One way of going, in addition to spray foam, is there are products made by some SIP manufacturers that can be used just for this purpose of the band joist. Remember, SIP is structural insulated panel, and they are pre-made insulated assemblies with a polyurethane foam core sandwiched between two pieces, typically of OSB, although it could be sometimes plywood. Also, we talked about how difficult it is to insulate on the flat. One way to go that can be done is to insulate the full space with an insulation installed carefully at proper density and with the necessary blocking at all the gaps between the framing members. In this case, you can see the footprint of the room above and the blocking and all the necessary gaps in the I-joists. As you can see with this installation, it takes a lot of insulation to fill the space between the. Another way to go is just to use spray foam to the depth you need for the required R value. Another way to go even further is, again, the structural insulated panels can be used, which will absolutely ensure grade 1 insulation and full alignment at the floor. Again, lots of options. We care about the what, which is grade 1 at the floor, and it's a very difficult detail, so we like to show you these ideas for how to use more advanced tech. And also, a key place to get the insulation right is at the openings between the house and the attic, so big thermal hole. One of the common ways of doing it at a hatch is to adhere some traditional batt insulation to the hatch itself and then put in the weather stripping gasket around the perimeter. This will work and is acceptable. Our concern, of course, is the longevity, as over several uses these details tend to suffer from damage. Another way to go is to use rigid insulation, which would be more durable than the batt, along with the same gasket material. Or they even make SIP panels specifically for the purpose of an attic hatch. They're pre-cut in size for the hatch, and it's an excellent. We also talked about the difficulty of slab edge insulation, or the importance of slab edge insulation to complete the system. You know, the slab is, when the edge is exposed, is like a superhighway for thermal flow that drops the temperature of the slab and creates a lot of comfort challenges in home construction. So you can do the slab edge insulation on the inside that is shown here, or you can bevel the edge if you think you need to put in something like carpet tack strips or glue flooring to a floor, and the insulation itself won't be a proper material to have for that purpose. So this is why this insulation is bevel. The other thing you can do is put the insulation on the outside and cover it with a protective layer like a fiber cement board or a metal flashing piece or a stucco parging. Where concerns of termites exist, there are details to address that. But essentially, you have to decide inside or outside where to put the slab. Now, even if there's post-tension slabs, we expect the slab edge to be on the outside of the slab as well in this case. Now, air barriers are absolutely critical for insulation performance as well. Here's the attic knee wall. We expect the backside air barrier. Anything that's meets the fire code requirements and creates a solid air barrier surface works. OSB, sheetrock, thin board sheathing. There are even insulation products made that have a FSK foil finish that can be used and provide additional. Air barriers are also critical throughout any conditions where the construction detail would leave exposed insulation, such as behind a tub or shower. Here you can see the coordination was done to make sure that the thin board sheathing was put in before the tub was put in. Normally the tub goes in right away after the framing. Then it's nearly prohibitive or impossible to get an air barrier behind the tub or shower. So very important to get at any condition where the insulation will be exposed on an outside wall. In climate zones 4 and higher, the interior. Also in all climate zones, you have to have the air barrier at any drop ceiling. Again, we showed many examples before the problems that can occur when that is not addressed. Any material that creates an air barrier will work. On the top you see sheetrock, where it's taped and spackled to seal the seams, or OSB shown on the bottom image with, again, caulking to seal the seams. Air barriers are also required at the attic eave to stop wind washing through the edge of the insulation. In this case, cardboard was used to serve as as a wind baffle. If you're in severe wet, you want to consider using more durable products like foams and plastics. But in any case, an air barrier is required in the form of a wind baffle at attic. Then thermal bridging is being addressed with a complete thermal enclosure system. There are 5 options for how you can handle thermal bridging at walls. One of them is advanced framing. With advanced framing, you'll be doing 2 stud corners. Use drywall clips or furring strips to provide the extra nailing surface for sheetrock, but this enables the insulation to run all the way to the corner. It also ensures that the sheetrock meeting at the corners, both pieces are attached to the same piece of wood to reduce. Here's a detail where interior wall meets an exterior wall. Again, we need to make sure insulation can go behind that assembly. So here, a lattice work was used with furring strip that enables that to happen. There are other details you can use with 1x6s, or what you can do is leave a 1-inch gap between the interior wall and the exterior wall and slide the sheetrock behind that and a metal strap on the top. Lots of innovative details will come up. It will save wood and first costs. It will allow more effective insulation. It's all improves the performance. So one way to go, we mentioned, for wall framing is with advanced wall framing that substantial amount of wood. In addition, as part of that set of requirements is insulated headers. Here is insulation installed on the inside, which is the recommended side by most building science experts to minimize cracking, but it also could be a sandwich of rigid insulation between two headers on either side of it, but you need an inset header. And the second option for doing the thermal bridging at walls is to use rigid insulated sheathing on the outside, where advanced framing will get you about a 12-13% framing factor, which means that's how much wood's exposed from inside to outside. What rigid insulated sheathing does is provide a complete thermal break everywhere but the apertures. So it's like it's a 0% framing factor, and it's a great detail for high. And the three other systems you can do. You can use structural insulated panels, will reduce thermal bridging substantially, as will double wall framing on the upper right, and the lower middle is a insulated concrete form or ICF wall assembly. These are all more exotic systems that work great but are less mainstream. Hopefully they'll become more mainstream. And then on top of that, wall assemblies being set up for reduced thermal bridging, the attic eaves have to have less thermal bridging. One way to go is shown here is with raised tail trusses that get R value at least up to R21 in climate zones 1 through 5, R30 climate zones 6 through 8. And those are the levels specified on the prescriptive tables in the IECC 2009. Another way to go if raised tail trusses are problematic for a builder is to use a higher R value plug right above the wall, and again to maintain R21 in climate zones 1 through 5 at the inside face of the exterior wall, or R30 at the inside face of the exterior wall in climate zone 6 and higher. And what spray foam or a high density blown-in product will do will often get you R4 to 5 or 6 per inch and enable that detail to work. The last part with thermal bridging is if there are any platforms in the attic, the same insulation requirements exist there as for the attic eave, R21 in climate zones 1 through 5 and R30 in climate zones 6 through 8. These platforms may exist for the HVAC equipment or simply for walking in the attic. And the last part of the complete thermal enclosure system is a high performance window. Typically it starts with the high quality low E glass, often with gas fills. Warm edge spacers improve performance, improve frame technology that reduces thermal conduction through the frame. So all these details work together to make high performance. So we have an amazing value proposition here for version 3 homes. We're going to compete with used homes, often that can be as bad as the image shown on the left, and be able to offer home buyers almost near thermal defect free homes like the one on the right. And essentially it will be incredibly visibly better quality. No question consumers are getting better homes with these incredible thermal enclosure details in every home. On top of that, the superior comfort and health that follows will be highly desirable, and one can only think about the resale value for the home on the right versus the home on the left, as this kind of comfort, quality, and health become the expectations and the norm that people expect in new construction throughout the country. This takes us to the next system, HVAC quality installation system, that's part of Energy Star version 3. And it begins with efficient equipment, right sizing, air distribution, and refrigerant charge that address the performance compromise we accept with current practices of HVAC systems, where we may pay for 13 and get 8.5. Now with right sizing we get better, with airtight ducts we get better, correct flow through the ducts, and refrigerant charge we pay for 13, we get 13. And all this is done with a very detailed checklist for the contractor and for the HERS rater. Now, one of the things the HERS rater will be doing is walking the ducts to make sure that they're installed properly, without the crazy bends, without the long lengths that are unneeded, without the compressions. The duct systems will be walked and verified to be installed properly, also with the proper. Also, the boots will be checked to make sure that they're airtight to their assemblies and not with big gaps so air can leak and go into the interstitial spaces. And pressure balancing will be assured with either a transfer grill, as shown here, that lets air out of the bedroom, 1 inch per 1 cubic feet of airflow into the room, and These transfer grills have both visual and sound privacy baffles that are very important, and they enable the air to get out of the room. On top of that, sometimes these transfer grills are installed above the door, and again they let the air get from inside the room to outside them. One of the ways to make the transfer grills, I think, more attractive in the future, I would look to entice the door industry to consider, is to actually make pre-hung doors with transfer grills built in, so that no installation would be required at all, just the normal pre-hung door, probably at a 7.2 height instead of a 6.8 height or even higher. And again, the air can get from the bedroom to the central. And the second way you can do air out of the bedroom to the central return is with jump ducts that let the air flow through a duct that goes from the bedroom through the attic back to the hallway. This works equally well, again 1 square inch per 1 CFM of flow. Big issue I raise with these is that it's 2 more penetrations into the attic, and it's only, you can only imagine the compromise you take when the attic's at 140 and the airspace in the ducts will basically be a conduit for the heat flow to the rooms in the summer and the cold in the winter. So I do prefer transfer grills, but right now the key is to get the air from the bedroom to the central returns. The third option is just to use a dedicated return from the bedroom to back to the air handler. Ventilation is required now in every home per ASHRAE 62.2. That's 7.5 CFM of flow per bedroom plus 1, and 1/100th of the square footage CFM. So in a 2,000 square foot 3-bedroom house, 3 bedrooms plus 1 is 4 times 7.5 is 30 CFM. 1/100th of 2,000 is 20 CFM. 20 plus 30 is 50 CFM. So you would be required by ASHRAE 62.2 to have 50 CFM of effective flow, continuous ventilation in the house. This can be done with an exhaust-only system as shown here. Continuous operated fan operates so quietly you don't know it's on. The way this works is it pulls air from the house out, in and out at exhaust. The air makeup has to come through whatever leakage is remaining in the thermal enclosure. So not ideal, because the air coming in the house has to come through cracks and holes, but it's an acceptable system and a low-cost system. Low-cost system is to have a duct that allows air to flow from the exterior into the return side grill in this case, or directly to the return side entry point of the air handler. And what this does is when the air handler is operating, it's pulling air from the outside as well as from the house into the central air handler unit. What's good about this system is that the air coming in is dehumidified and conditioned, so it can be more comfortable, and it's low cost. The other issue the negative issue about this system is that that the house goes into slight positive pressure, and what completes the cycle of air being pushed out to make up for the air coming in is the air has to go out again, the remaining holes and cracks. So it's not complete control, but it is lower cost. The other thing about these systems is that if they only operate when the air handler is running, there has to be a controller that makes sure the air handler operates X number of minutes per hour as required to assure the ASHRAE 62.2 specified airflow. Now, what you could do is combine both of these low-cost systems for a low-cost balance system, or you could have a more expensive balance system, pre-made enthalpy recovery ventilator or heat recovery ventilator. The way these systems work is the airstream coming in exchanges heat with the airstream going out. If it's an enthalpy recovery, there's also a media exchange pad, so the moisture coming in can be exchanged with the moisture going out in the summer. In the winter, the moisture going out can be exchanged with the dry air coming in the winter, so the house doesn't go too dry. So these are much more expensive systems, but all of them meet the minimum requirement 2.2. In addition, spot ventilation is required in bathrooms, at least 50, and in kitchens 100 CFM. And then filtration is required that works. That's at least MERV 6 and is installed in a frame that does not allow air to bypass the intended purpose of the filter itself. What's revolutionary about Energy Star version 3 is for the first time now we can approach the HVAC industry and say these widely developed and accepted standards by the industry association and the manufacturers that we have not been following can now be followed with complete confidence. That is an amazing development. HVAC installers rightfully were concerned that they needed to do bigger systems when they were held responsible for all the failures of thermal enclosures. Bonus rooms over garages, cantilevers, southwest bedrooms that were not installed with good low-E windows that had too much solar gain. Anytime there was a comfort problem that was really a function of the thermal enclosure, they were held accountable, and they became naturally reluctant to do quality installations. On top of that, pressure to keep reducing costs also reduced the amount of training time and resources available, and also minimized the effort they're willing to make to install systems properly. Now, with version 3, with nearly thermal defect-free thermal enclosures, we can go to the HVAC industry and with confidence for the first time, they can always do a quality installed system. This is a revolutionary concept. They have something they never had before. So, the value proposition for HVAC is basically you're going to now finally get what you pay for when you buy a heating cooling system. You pay for CF15, you will get 15. If you pay for 94% AFUE, you get 94%. And you'll get something that every home buyer deserves. When you spend $200,000, $300,000, $500,000 for a new home, you should have engineered comfort. Thermal comfort, humidity control, noise control. And lastly, you should have fresh filtered air in every home. There isn't probably hardly any homeowner that doesn't want fresh air in their house and doesn't want particulates filtered out of the airstream. For the first time, we get this effectively in every Energy Star home. And this takes us to the last system in Energy Star version 3, the water management system. And the first part of a complete water management system is water managed roofs. This includes heavy roof membranes at all penetrations and valleys. At a valley, you can have 100 times more concentration of moisture than you do at a single point on a roof above. The valleys are critical to have installed with heavier gauge. In addition, in cold climates, we require membrane material extending 24 inches inside up the roof so that it's 24 inches away from the inside face of the exterior wall. This is critical because of the extra abuse in cold climates with snow and heavy winter weather. So this is one requirement as well. In addition, any exposed roof sheathing should be protected with drip edge flashing. At walls, we should have the kick-out flashing so the water is diverted away and not against and behind the siding. It can be done simply with one more piece of step flashing that's bent and diverts the water away. There's some indications that these may corrode faster than they should. Advanced materials like pre-made plastic diverters that take the water away from the wall, but all that matters, at least some diverter details provided to get the water away from running behind the wall surface. Every window and door must have a pan flashing detail. One of the lowest cost methods is to use a fabric material. There are other more expensive pre-made plastic materials that also have slopes or back ridges to stop the water from extending to the backside into the house. But some form of pan flashing is required at every wall. And then every wall must complete the picture with a complete weather-resistant membrane, properly coordinated with the flashing at the windows, and drain completely to the ground in a shingle fashion. And that can be house wrap as shown in the previous image, or old-fashioned building, and or the rigid insulated sheathing, if that's being used for thermal bridging, can often be taped and be the exterior weather-resistant membrane. At the foundation, the drain tile has to be wrapped with a fabric filter. One way to do it is put the fabric filter down, the gravel, the drain tile, more gravel, and then complete and loop this whole assembly with the fabric filter so the sediment can't get in. The way to do it is with pre-made drain tile that comes with the fabric filter wrapped around it. There has to be fabric filter at the drain tile in climates that are designated as well. And also in climates that have wet climate conditions, we have to have a capillary break under the slab. and that's gravel and or sand, and poly and or geotextile. Now in climates that aren't wet, they have an exemption from this detail, and in climates that have slab on grade construction, the gravel is forgiven, but the capillary break, the plastic, is required. And in crawl spaces, they have to be also lined with a capillary break. One of the benefits of these capillary breaks, by the way, is that they provide the first key step to an effective radon resistant construction system, which is gravel and poly, that stops the ability for radon gases to migrate into the home. And as you can see in this map, there's just extensive amounts of the country exposed to high levels of radon. And then lastly, site drainage. The house has to be drained next to it, so the water runs away from the house as opposed to next into the house. And then on the inside, materials have to be selected and used properly. Here shows a vinyl wall covering material in a hot, humid climate. The primary driving force is a hot, humid outside air trying to get inside where it's lower humidity and much cooler. And when it hits a surface like vinyl, which is a vapor barrier, it hits a dam, and the water just keeps collecting and can lead to mold and mildew, as shown in this picture. So the proper selection of materials is very important. And protection materials in wet climates is also required to ensure they don't go into the house already moldy and wet. So the value proposition with the water managed construction is that we get better protection for the largest investment of most people in their lifetime. There's much lower maintenance with this kind of protection, and because you have much less likelihood of mold and moisture problems, a much healthier home. So here we are, Energy Star version 3. Complete systems equal assured performance. In an existing home and an Energy Star home, we always want a comfortable indoor 70-degree environment. But the thermal enclosure defects are so much greater in the existing home than the Energy Star home that we need much bigger systems, and we experience much colder surfaces. Whereas the Energy Star home, we use much less energy, and we have complete control of the surface temperatures for much higher grade comfort. Then the HVAC system in existing home often is installed oversized and is much noisier, has less effectiveness, has many problems with how the duct distribution systems work. In an Energy Star home, a much smaller, high efficient system with effective distribution of the heated and cooled air is installed in every home, and there's a complete whole house ventilation system and spot ventilation system. And then water protection often comes in parts in existing homes with key details missing, like the kick-out flashing or fabric filter, whatever it may be. With Energy Star home, water protection is a system. Roof, walls, foundations, materials, all part of a complete water protection system. Energy Star for new homes has arrived with version 3. This is an incredible value package for every homeowner. This will take new home construction to the next level, incredible place for new homes to be. I encourage all builders watching this webinar to join us in this program, those that are already members to continue working with Energy Star as its value keeps getting better and better. Thank you all very much. This is Sam Rashkin.